Okay, here's our second circuit. This one's going to be a series circuit. So remember, it's going to follow a couple different rules and formulas than what we had previously. So let's take a look at which ones those are before we get started. So when we're solving for the impedances or the voltages, we're only going to be using these two triangles here. But we can also use the power, which works in all circumstances. So we just want to stay away from the parallel rules here. And if you're not a trig person and you're more of the formula kind of guy, you can take a look up here and see some of these. So we'll be using Pythagorean theorem for the impedances, and then that'll work as well for our voltages. Again, these are just two sides of the same coin. If you visualize it as a triangle, you can use you can see how you can use Pythagorean theorem, or if you're visualizing it as a formula, you'll just have to remember how to calculate your phase angle. All right, let's go back and start our circuit. So the first thing I'm going to do is copy a couple of those values down. So for 10 volts, that's our voltage total. For resistance, we have 5 ohms again. And for our inductor, what I've seen a couple guys doing, what you don't want to do is go ahead and take that 10 and write it in here, because that is not your resistance value. That is your henries. That's your inductance. All right. There was quite a few mistakes yesterday on that, so let's just remember we got to convert that. We did a lot of problems practicing converting this for a reason, and that was to remember we have to convert that to the reactance in order to apply it to an ohmic value. So if we're looking at converting that, that's going to be called XL. Right now it's just L. Let's go to our formula sheet and look at exactly what formula we'll be using here. So we're going to be converting from L to XL. So we want to solve using this equation right here, not this one, because we have L and we're going to be plugging that in. So 2 pi frequency times the inductance. Our frequency is 60. And our inductance is 10 millihenries. So let's go ahead and just convert that now. So 3 zeros for the milli. Sorry, let me correct myself there. Thinking of micro from the farads. So since we have milli, we have 10. We're going to move it over 3 decimal places. And that's going to give us 0.01. So 60 times 0.01. So let's put that in. 2 pi times 60 times 0.01. That's going to give us inductive reactance of 3.7, say 3.77. 3.77 ohms. Put that in the right category. Okay, so the next step we could solve for would be our impedance, right? Because we have two other values. So if we're using the triangle method, we're looking at a triangle, and we have the 3.77 and we have the 5. Now we're looking for the impedance. So we're not going to just be adding those up like in typical series circuits. We're going to be using Pythagorean theorem for that. So if we want to look at our formula sheet, or if you already know it, we're going to be looking at the impedance, right? So that's going to be right here. So R squared plus XL minus XC, this is only inductive, so we're only going to have that squared, and we're going to find the square root of that. So Z equals the square root of 5 squared plus 3.77 squared. Okay, let's go ahead and put that in here. So square root of 5 squared plus, oops, 3.77 squared. That's going to give us 6.262. So we have now two values in our total category. So with the impedance and the voltage total, I can easily locate what the current's going to be. We're just using simple Ohm's law now. So 10 divided by 6.262, that's going to give me 1.597 amps. Now we have a series circuit again, so one of these values, either the 10 volts or the current, is going to be the same across all of the components. In a series circuit, that's going to be the current. So now we can find the voltage drop on both components because we have both the resistance and the current in the resistor, and then we have the reactance and the current for the inductor. So that's going to be just multiplying those two together to get the voltage, right? So I'll have 1.597 times 5, and that's going to be 7.985 for the resistor. And then I'm going to have 1.597 times 3.77, and that's going to be a voltage drop of 6.02021 voltage drop on the inductor. Now, what's a way we could check our work here? Make sure we didn't make any errors up to this point. Well, if we look at our formula sheet, our voltage triangle applies in series circuits. So just like I use Pythagorean theorem for my impedance, I can also use it now for my voltage. So let's go ahead and plug this in and just check our work there. So that would look something like this. My voltage total would be the square root of 7.985 squared plus 6.021 squared. And that gives me pretty darn close to 10 volts. So we're looking good there. So now we're going to be looking at the power. Now, the one I usually use is the current and the voltage, because to me there's no square roots or dividing or anything. You just multiply the voltage times the current. So I'm going to go down the line and just do that. So I'm going to have 10 times 1.597, which is a 15.97 volt amps. I'm going to have 7.985 times 1.597, and that's going to give me my watts and my resistors, because that's the voltage times the current. And that's me 12.752. And then we'll do the same thing here. So 6.021 voltage across the inductor multiplied by 1.597. That's going to be 9.616 VARs. Now, I could also check my work using the same triangle across all my power circuit. So my true power, my VARs, and my apparent power, that triangle, just like on our formula sheet, would look something like this. So my VARs, watts, and voltamps, and my triangle itself would be 9.616, 12.752, 15.97. So I could solve this any which way I wanted using the voltamps or the watts and just solve for a missing value. And as long as it works out, other than a couple rounding errors within to get the same number, then you should be fine checking your work with that method. So the last two things we have here is our power factor and our phase angle. So power factor, the formula we use most often, is just going to be our true power divided by our apparent power. So if we put that in, so it's a power factor of about 0.80, we'll say. Usually we only do power factor in 2 digits. Go ahead and round there. Now, if we wanted to use the same data, which if we go back to our formula sheet, our phase angle, we could use a variety of different methods here. We could find it within the series circuits based on our impedances. We could find it based on our voltages, or we could find it based on our power. Now, this is the tried and true method because it works in both series and parallel, but whatever cleaner numbers you had or whatever method you wanted to use, they should all come out exactly the same, no matter what you're solving for the phase angle. So that's going to be, if we looked at our triangles, the adjacent divided by hypotenuse, which is going to be cosine. So cosine inverse of 12.752 divided by 15.97. And if we put that in, inverse cosine or arc cosine, 12.752 divided by 15.97, we're at 64.6 degrees. So here we've solved for all the missing values. We'll do a couple harder ones where you start off with power factor or phase angle and less values in the circuit. But this is just an overall view how you can check your work and how you can get through these series ones. So I'll do a couple more challenging ones coming up. I'm going to try and get these ones online sooner rather than later, so you might be getting a couple emails from me. But take a look, and if they help you out, let me know and I'll keep them coming.